And I'm going to be talking about water-activated polymers in a number of different sectors, including healthcare, energy, and environment. I won't spend very much time on energy, but I will give you a taste of what we're able to do. I'll spend most of my time regarding healthcare and environment. So, the first thing is to acknowledge the people who did the work. So I have several collaborators at NC State. I also have collaborators at other universities, including the Norwegian University of Science and Technology, Boston University, Kansas State University, and the University of Oregon, now relocated to Berkeley. But this has been a multi-year process where we've more or less showed that we can use water activation as an efficient way to enter into these different sectors in a very non-compromising, safe, and effective way. I'd also like to just point out my partners and sponsors of this research. You can read them here. I'm not going to go through them with you. But again, a very broad scope here. And now let me begin with the healthcare. So there are two different microbial issues that we need to consider in our daily lives. The first one was the one that we encountered during the COVID-19 pandemic. This was an acute problem. This is the one that caused a number of unnecessary deaths around the world, many of which have not even been fully reported. And it comes at just different time periods for a relatively short time, a year, 2 years, maybe 3 years. We've seen this before. So this is the acute problem. The chronic problem deals with the increase in the number of drug-resistant microbes, which are collectively and colloquially referred to as superbugs or nightmare bugs by the popular press. And these are the ones that become problematic because it is predicted by the year 2050 that the number of deaths due to these types of infections will increase beyond the total number of all different types of cancers combined. So it gives you an indication that this is something that is on the horizon that we really do need to pay attention to. Now, I've listed a few of these types of microbes shown here. These are listed according to the U.S. Centers for Disease Control and Prevention, CDC. And some of these are urgent threats, some of these are less so, but in all, these can be very problematic and they are all subject to developing antimicrobial resistance. Now, you might think that most of these are really found in developing countries. That's not the case. If we look at MRSA, methicillin-resistant Staphylococcus aureus, that is primarily found in the US, in South America, in Western Europe, Northern Africa, Australia, and we don't have data from Russia and China. So these types of drug-resistant microbes are ubiquitous around the world. And, well, quite frankly, we need to find a way to deal with them. So here are a number of different conventional strategies. One could focus on a particular type of microbe and then develop ways of targeting certain chemistries on those microbes. But these are the ones that usually lead to antimicrobial resistance. One can start thinking about biomimetics, such as, for example, developing corrugated and hierarchical shark skin, where you have controlled roughness on the surface. You could also think about changing processing or environmental conditions, as you see here. But lastly, we're going to take a materials approach. And yes, we could talk about putting in carbon nanomaterials or nanoparticles. And we could talk about developing super hydrophobic or super hydrophilic surfaces or introducing photosensitive dyes that yield reactive oxygen species such as singlet oxygen. But I'm going to turn our attention to charged polymers. And for those of you who are familiar with charged polymers as antimicrobial materials, I'm going to say that what I'm going to show is going to be a bit different. So let's now take a quick peek at what is currently used. So when we think about cleaning a surface, the first thing we go to is, of course, a disinfectant. And the disinfectants are typically quaternary ammonium compounds, quacks, as they're referred to. And these work. These can certainly work within a couple of minutes. But the problem is that you have to have someone who applies this and the surface doesn't stay clean. And so it's a point in time solution, not a continuous solution. Moreover, during the pandemic, so many disinfectants were used that they actually compromised the environment. We could talk about using radiation such as UV, but once again, it's a point in time solution and it also can damage healthy cells. So we talk about now self-cleaning surfaces where we might put in copper, silver, nanoparticles, or maybe titania or zirconia nanoparticles, and they work. But microbes, especially bacteria, can develop resistance to these. And what's worse is that polymers are abraded. That is just the nature of polymers. And so when this happens, these particles can be released into the environment. And if they do, they can enter into the food chain. So that's problematic. We can then talk about either coating the surface of an object or even growing polymer chains off the surface. And this works insofar as the surface remains intact. If it is compromised via, for example, abrasion or cracking, then once again, we have a problem. And lastly, here's one type of charged polymer that has proven useful. These are cationic polymers. They're positively charged. And the reason why these are so nice is that they attract negatively charged bacteria. The outer membranes are negatively charged. And so by doing so, then these bacteria can have their membranes sliced and basically we can kill those bacteria. Notice I did say bacteria here because this isn't necessarily a viable way to deal with viruses. So I'm going to switch over to a different type of material. This is an anionic polymer, and to be more specific, it's an anionic block polymer. So just to make sure that we're all on the same page, the block polymer has contiguous sequences along the polymer backbone. These are very discrete so that we can impart the functionality of those sequences into the polymer. So the end blocks that you see here are T-butylstyrene, denoted as T over here, and they are glass-forming blocks. So this provides the materials with strength. The intermediate blocks are hydrogenated polyisoprene, otherwise known as ethylene propylene rubber, denoted here by E. And this is what gives the material flexibility. And then the middle block is partially sulfonated polystyrene, S. And the red units that you see here are hydrophobic. The middle block is hydrophilic. So this is, in fact, a thermoplastic elastomer. It does have elasticity associated with it. And I will point out that in addition to referring this as T-set, we're going to put an X after it to denote the degree of sulfonation. What's unique about this material from a polymer physics standpoint is that you can change the morphology of these self-assembling materials simply by changing the solvent. So we can either have, as you see over here, coexisting alternating lamellae and hexagonally packed cylinders, or we can have dispersed ionic domains down here. Over here, the ionic domains appear dark because of selective staining. Here, the contrast is reversed, so you can better see those domains. So that's one thing. They're solvent templatable, but these materials cannot be subjected to thermal annealing. So instead, we use solvent vapor annealing. And what that means is that we take a polymer film, it's a bulk film, so we're looking at from a half millimeter up to a couple of millimeters thick, and we subject that to the vapor of a solvent at room temperature. Now, just to put things in perspective, the glass transition temperature of these end blocks is about 130 degrees centigrade. And so room temperature is far below that. But what you see from these real-time small angle X-ray scattering profiles, we can start off with this morphology that you see here. That's this profile at time t equals 0. And then every one of those profiles is collected at 2 minutes. And you can see that when we get up here to 6 minutes, the profile has changed rather abruptly and remains the same throughout the rest of the experiment, with those peaks becoming sharper and more numerous, and finally ending at the end of the experiment with 6 orders of reflexes. This is a highly, highly ordered material. And if we analyze those profiles, or alternatively look at transmission electron microscopy once again, we see that this is what we produce. So this morphology changes to this within minutes, just based on solvent vapor annealing. Okay, so this is going to be initially the prime player in everything that I talk about. Okay, now let's go ahead and see about the surfaces of these materials. Because if we're talking about antimicrobial properties, then we're talking about surfaces. So this is an ultra high resolution, low voltage SEM image showing that those lamellae extend to the surface. These are complementary AFM images where we have height and phase. You can again see those structural elements on the surface. In terms of the chemistry, if we subject the polymer to phosphate buffered saline solution, which is typically what we use for application of microbes, we see that we have an increase in the sulfur and oxygen peaks. So the sulfonic acid groups are at the surface. And lastly, just to put things in perspective, this is what we find. This is now the survival of MRSA, which is a highly drug-resistant bacteria. And if we have 52 mole% of this polystyrene mid-block sulfonated, we can get down to minimum detection, which is a 6 log unit reduction. So we're talking 99.9999% inactivation within 5 minutes of exposure. And that's simply due to the fact that at the surface, we have these structural elements that provide pathways. Note that if you go to a typical disinfectant, it'll say about 2 minutes. So we are well within that, but the big difference is this is not a point-in-time solution. This is continuous. This is self-cleaning, and it does not add to solid waste. So the mechanism is very simple. Upon hydration, protons from the sulfonic acid groups within the block copolymer migrate to the surface. They force the contact layer, the aqueous contact layer that resides at the surface, to decrease in the pH. How low? Well, what you see here, let's look at just cycle 1 for Staphylococcus aureus. Here's that 5-minute exposure and 6 log unit reduction. And you'll notice that the pH is about 0.8. That is significantly lower than your stomach acid. So this highly acidic environment is what causes almost immediate demise of the microbes that we tested. Is it safe? Absolutely. This is a hydrated polymer sample. When one of my students is touching it, there is no sensation of acid because the layer, that contact layer, is only tens of nanometers thick. And so you can't feel it. Now, I don't recommend licking it or putting it on your eyeball, but for all intents and purposes, it is safe to handle. So let me give you a couple of quick results. For those of you who are unfamiliar with the escape family of bacteria, these are 6 different bacteria that are primarily responsible for hospital-acquired or nosocomial infections. They're listed here. Some are gram-positive, some are gram-negative. Gram-negative bacteria are more difficult to kill than gram-positive because they have a secondary membrane. But you'll notice that in all cases, for the 52 mole percent polymer, we get to the minimum detection limit within 5 minutes. And we can boldly claim that 99.9999% plus, because we can only measure to 10 to the minus 4 down here, is about 100% kill. This is what it looks like for MRSA and for E. coli. This is ampicillin-resistant E. coli, so it's also drug resistant. And you'll notice that the controls look very reasonable, as they should. But then after 1 minute, 5 minutes, and 10 minutes, we see the bacteria essentially dissolving. If after 10 minutes with MRSA, we had a hard time even finding cells. And in the case of E. coli, we see that the outer membrane that's perforated remains. We didn't stop with those bacteria. We also went on to C. difficile. This is an urgent threat, and it is primarily responsible for the deaths of elderly patients and those who are immunocompromised, especially after antibiotic treatment. This is the bacteria that killed my mother when she went into the hospital with a diabetes infection. And it is highly resistant to a variety of different types of cleaning mechanisms. Well, we looked at 2 different strains, one which was hypervirulent, and we found that between 5 and 10 minutes, we were able to completely inactivate the vegetative state of C. difficile. This is where it becomes contagious, and we actually got more than 10, we got more than 6 log units reduction. And these are the SEM images, and once again, we see intact and only the husks from the outer membrane remaining. The same material can be used for fungi. And so we've looked at the Candida fungi, both albicans and auris. Auris is considered an urgent threat by the CDC. Both of these can be found in the GI tract, and C. auris is also prevalent on skin. And so you can see that, again, within short time periods, the fungi are decomposing, and according to these photomicrographs, there is considerable blebbing that occurs. Most people, when they think of microbes, they think of viruses, so we can do the same. We started off with several viruses that you see here. Human adenovirus was the one that showed the most resistance, but influenza, not a problem. And then we, of course, turned to SARS-CoV-2 with the help of our colleagues at the National Emerging Infectious Disease Laboratory at the University of Boston. They have a BSL-4 facility, and so we were able to test SARS-CoV-2 there and found that our polymer was far more effective by at least an order of magnitude compared to copper. In fact, here are the results from copper that were published in the New England Journal of Medicine, and you can see that even after 4 hours of exposure, the results are nowhere near what we could get in 5 minutes. And this is just, again, a repeat with a different variant of SARS-CoV-2. I believe this one is the XBB 1.5. And you can see that once again, when we get to 5 minutes of exposure, we can basically say that we have completely eliminated SARS-CoV-2. Now, I focused on this polymer, but we can actually use other polymer designs. These are specialized and they work very, very well, as you can see here, as long as we have sufficient sulfonation. So if we only have 17 mole percent, it's not enough. We don't have enough protons available to inactivate the microbes. But we can also go to a more generic polymer. This one is available in from many different distributors, and it's relatively inexpensive. And so we can, in fact, sulfonate the end blocks of this material, noting that if we sulfonate too much, then this polymer will dissolve in water. But if we keep it at 44 mole percent, we actually have a stable surface, and it also works quite nicely. Now, the one thing about academic research is that we usually have our research within our laboratory, and then we say it would be nice to be able to take this and put it into applications. Well, this material was put into application. It was granted emergency approval in 2021 by the US Environmental Protection Agency so that it could be used by Kraton Corporation, which licenses the technology from my university, and it could be used by Delta Airlines in their terminals domestically. So here's the announcement, and here are the announcements of how it would be used. So it was put as a coating on ticketing terminals and ticketing counters, so that when people touch these with their fingertips were being cleaned without them even knowing it. So this actually allowed us to field test this material, and it identified other issues that we needed to address, and which we have since. Okay, now let me jump a little bit because I told you I'm going to be talking about different sectors. So I'm going to just mention this in passing, but we could use the same polymer in the energy field. How? First, we can make solar cells from these materials very, very easily. We can make simple ones that mimic leaves, and so current densities are low, on the order of microamps per square centimeter, and efficiencies that are laughably low, but they do mimic leaves. If we wanted to make something that was more commercially relevant, we could make dye-sensitized solar cells, which is what you see here. Now, current densities are in the milliamp per square centimeter range. We're looking at fill factors of about 70%, and we're looking at efficiencies of about 7%. So, and that's non-optimized. In addition to that, the incident photon conversion efficiency that you see here indicates that we're collecting photons over a very broad wavelength range. So these materials have a lot of promise, and they're their own adhesives. So we don't have to start putting in additional components to these materials. And recall, they're thermoplastic elastomers. They are flexible. We can make batteries out of these, and we have lithium-ion batteries, where the material that I've been talking about is used as a separator, and we find that we can get, after 1,000 cycles, so this is about roughly 4 years of use, we can still get efficiencies that are close to 100% and capacities that are about 75%. This is on par with some of the best lithium-ion batteries out there. And again, this is not optimized. And we, again, rely on transport through those amphiphilic channels that I showed you in the TEM and tomography images. Lastly, we can make bipolar electrolyzers. And in this case, yes, we need to have a catalyst. And so the catalyst that was designed here was a tin oxide catalyst, but it was only 3 nanometers in diameter. So it had a very, very high concentration of surface atoms. And what we found was if you look at the overvoltage as a function of current, our results from this polymer, which is shown here as TST, were on par with Nafion. And it's important to realize Nafion is fluorinated. So it has that negative connotation with it. Our material is non-fluorinated. So it's a safer material to use as well. And it's a lot less expensive than Nafion. Okay, so I'm sorry for just briefly talking about this, but again, my time has been cut short, so I will progress now to the environmental issues. And in particular, I'm going to be talking about CO2 removal. Now, there are lots of reasons why we want to consider removing CO2. The most obvious of which has to do with climate change. And I won't spend much time talking about that because everybody, I think, is well aware of that problem. But what I will point to is that there are other reasons why we would want to remove CO2. For example, we could remove CO2 from methane because CO2 is often pumped into methane wells to remove the methane. That means it has to be separated. It's a process called methane sweetening. Or if you look at hydrogen, most hydrogen is produced commercially by the water gas shift reaction. And in that reaction, we have a mixture of CO2 and hydrogen. And hydrogen is not just a fuel, it is used in a number of different industries, ranging from pharmaceuticals to basic, all the way to fine chemicals, to steel manufacturing, fuel cells, etc., and food, of course. In addition to that, we have air purification as a consideration, especially if we're talking about extraterrestrial travel or colonization or underwater operations such as aquaculture. And of course, during the pandemic, we saw many pictures like this. Well, the way that these ventilators work, they have tubes that are used to separate out CO2 from oxygen so the oxygen can be recycled. And so this is another reason why we would want to selectively remove CO2. So we know about the carbon dioxide levels. I'm not going to spend much time talking about this other than we have already gone way past the target of 1.5 degrees centigrade increase by 2040. So that's kind of a moot point. In fact, these results that were published in Nature indicated that for us to get back on track for that would be basically would mean a precipitous drop in CO2 emissions. That's not going to happen. In fact, 2 degrees centigrade worldwide temperature increase is also looking rather bleak. And we have all seen the different symptoms of climate change, so I'm not going to spend time talking about those. But suffice it to say that we are deep within this particular challenge that we need to address. Okay, and I found this one rather interesting when I was talking to my colleagues who live around the Mediterranean Sea area, that they might encounter a tsunami at some point. So let me take just a quick moment. I don't want to get too far into background information. I want to basically get into results, but I think it's important to just realize that there are different mechanisms of transport through polymer membranes. So two important measurements, the permeability, which is throughput, and selectivity, which gives us a measure of separation quality. And in the simplest sense, the ideal selectivity is simply the ratio of permeabilities of the two species A and B that you see here. This is the performance graph. It's called the Robeson plot. And on this, we plot on double logarithmic coordinates the selectivity of CO2 to another gas, and we choose nitrogen as a mimic for air. And then we have CO2 permeability down here. And you'll notice that I have lines here to indicate what's called the upper bound. This is an empirical trade-off that basically says if you have polymers that give you high permeability, they're not selective, or if they're highly selective, they're not very permeable. Ideally and arbitrarily, I've identified this region up here as the Goldilocks region. This is where we would like to be, okay? And it is arbitrary, but it also provides an idea of where we should target. The mechanisms for transport are either solution diffusion, which is the most common. In this case, in the Fickian diffusive regime, our permeability is simply the product of diffusion and solubility. Or we have facilitated transport where the diffusion is reaction augmented. And we usually talk about transport being diffusion controlled or solubility controlled. And diffusion controlled membranes are typically glassy polymers, whereas solubility controlled membranes are usually rubbery materials. So, getting back to that block polymer that I showed you just a few moments ago. Here are results showing the water solubility and diffusivity as functions of the relative humidity. So this is the humidity of the feed in which we are incorporating CO2 or nitrogen. And you see that the water solubility is much higher in this material than Nafion. In fact, this material has a higher transmission of water than Nafion does. And its diffusivity is higher at high relative humidities. If we look at the permeability of CO2 from both single gas and mixed gas measurements, we see that very, very well behaved as a function of humidity and definitely on par with what you would have for Nafion. But it's the selectivity that makes a big difference because it continues to increase as relative humidity increases, whereas for Nafion it levels out. Just to put this in perspective, Nafion consists of amphiphilic channels, just like the block polymer, but they're much smaller, typically on the order of about 2 to 5 nanometers, whereas for the block polymer, they're on the order of about 20 to 25 nanometers. We could take these materials, start off with different solvents. Remember, they're solvent templatable. And what you see is that the results show that if we cast from THF, which gives us our alternating lamellae, we have the highest permeability, but the lowest selectivity. The others are kind of all grouped together. If we take these materials and simply put them into liquid water, we can induce a non-thermodynamic morphological transition such that we now have a greater degree of interconnected hydrophilic channels. And by doing so, the permeability of CO2 increases significantly up to about 500 barer, whereas the selectivity really doesn't change. And what that does is it actually gets us over that upper bound line that I showed you in the performance graph. It's not a significant increase over the upper bound, but it does show that it's possible to get above that upper bound using these materials. Can we do better? Well, the answer is yes. So I'm going to show you what happens when we combine transport mechanisms. So in this case, we're going to take solution diffusion and combine it with facilitated transport. We're going to use a high flux membrane, either polydimethylsiloxane or polytetrafluoroethylene in its amorphous form, not semicrystalline form. And we're going to add to it facilitated transport. Now, most polymer membranes, if they're self-standing, are about 50 microns thick. But that has been eliminated over the years such that polymer films are made much thinner, about 1 micron, but they're now supported on a macroporous support, so that when we have CO2 and nitrogen and water coming in, well, the water doesn't do anything because these polymers tend to be hydrophobic. The CO2 and nitrogen will enter into the polymer, and if the CO2 likes the polymer a little bit more, we'll get a bit more CO2 out than nitrogen. But we're going to do something very similar to a lab on a chip. This is an absorption facility that is located in Norway. It uses liquid amines to absorb CO2 from gas mixtures. We're going to take this absorption facility and we're going to put it right on top of this thin polymer film. So the way that we're going to do that is we're going to grow polymer chains off the surface and then aminate them so that we have the same amines here that we would have over here. Think of it as plant on film. And now, in the presence of water, this surface becomes highly swollen. It essentially becomes a nano sponge, and it loves CO2. So much so that now the amount of CO2 going through is much, much higher than what we have for nitrogen. This type of membrane we've called a hybrid integrated or high membrane. This is the chemistry. I don't have a whole lot of time to go through this, but suffice it to say that it starts off with hydrogen abstraction, and then we start to grow polymer chains off of these embedded monomers. And once the polymer chains are grown, we can do a little bit of substitution chemistry to introduce the amine groups. And these are the XPS spectra to prove that, yes, we are getting nitrogen on the surface. These are complementary AFM images where we have the height and the phase image. Over here, height is light. Over here, phase, soft means dark. And so these protrusions that you see here are actually quite soft. So these are more or less patches of these grown chains, and you can see them over here as well. This is, by the way, an ultra high resolution SEM image showing the same kind of features. Now, if we look at the performance, we see that initially the PDMS and PTFE have very high permeabilities, but very low selectivities. And after we aminate them, so that's what AM stands for, we see that the permeabilities drop a little bit, but the selectivities go up significantly. And we can do this also with CO2 and methane, and we see exactly the same kind of result. So it can be used for methane sweetening. So let's put this all together so that you can see this performance enhancement. Here are the starting materials, PDMS and PTFE amorphous form. These are polymers of intrinsic microporosity. So these are materials that are nanoporous. Okay, so that's why we have two different upper bounds that you see here. These are segmented polymers, basically block polymers, in which one of the blocks is a polyether. And some of these actually show tremendous promise. These are the only ones, though, that have been commercialized. If we want to look now at the materials that I've just shown you, this is where we are. So with PDMS, depending on the temperature, we can be down here, but if we increase the temperature, we can actually get into the Goldilocks regime. And for the aminated PTFE amorphous form, we're definitely high in this Goldilocks regime. So we get simultaneously high selectivity and permeability, low cost because we're using materials that are already used for making membranes, very simple manufacturing in terms of putting these or growing these polymer chains off the surfaces of the polymers. I didn't show you the data, but they are mechanically durable. They're stable over time. Even if they're dried out, they can be rehydrated and reused. They are process retrofittable so that new modules do not have to be designed for these materials. And they can be used in a variety of different applications with no additional waste than is already encountered. And just to kind of bring this full circle, I've talked about healthcare, I've talked about energy, I've talked about the environment. These are all related. So bacteria cases increasing following hurricanes, microbial outbreaks, and even the superposition of chronic bacteria and acute pandemics. So here are my conclusions. We have an unprecedented nexus of existential threats. And these are man-made for the most part, and they're highly interrelated. I've shown you how we can use material science, in particular polymer science, so that we can address healthcare issues, we can talk about energy issues, and we can talk about environmental issues. All of these are water activated, and that makes them very promising in terms of being put into service. So with that, I thank you very much for this time that you've spent with me.